AP Calculus AB, Unit 6 Day 8 lesson. So let's see. All right. So second derivative test. This is another way of calculating the relative maxes and mins. So this is second derivative test for relative extrema. Anyways, we have a warm up here. These 4 problems. So I'm going to go and try them all and pause the video and try them, and then I will go over them. And this will review some of the stuff we've been doing, which will help us with our new lesson today. So go ahead and try them. Okay, assuming that you've tried them, we'll look for relative extrema and determine x coordinates and determine their nature, meaning is it a relative max or is it a relative min? Because if I just want relative extrema, you could just tell me where they're all at, kind of more in general. But so our best strategy so far has been do a line check. 4x cubed minus 12x squared equal to 0 undefined. And factor it 4x squared out, x minus 3, 0 undefined. So x equals 0 and x equals 3. Now this one has an even exponent on it, so that's one's going to bounce off the graph. So we're going to do a first derivative line check. 0, 3, test a point. X equals 4, positive, negative, negative, stays negative. I like to draw these little arrows right here because these are all slopes. This is decreasing, decreasing, increasing. And this is a relative min right here. And this is neither. It's like a plateau. So we're going to say that we could say y has a relative minimum at x equals 3 by the first derivative test for relative extrema. So this is justification for it. I'm going to ask this sometimes. It's for sure required on free response. Well, okay, well, how? That's the name of it. Tell me how it works. Since f or y prime, I guess y prime is negative on 0 to 3, and f prime is, y prime is positive to the right on 3 to positive infinity. So that's a really good thorough answer with a good justification. Okay, so that's the most official technical way. This one right here, we're going to do, now always watch out for domain stuff. There's no domain here, there's no domain here. We're going to do a product rule here, and some chain rule and exponentials and powers, a bunch of derivative rules. So x squared times derivative e to the 2x is e to the 2x. Chain rule says take derivative what's inside. Plus e to the 2x times derivative x squared is 2x. And we're going to set that equal to 0 undefined. I'm going to start factoring right now. I think I can take an x and an e to the 2x out of everything. That would leave a 2x, and I could take a 2 out also. Leaves an x plus 1. So x equals 0, x equals negative 1. There's nothing that will make that go to 0. These are critical points. And, sometimes it's for response, I probably write out critical points, write it all the way out. CP is kind of a lazy way of just showing that in your work. We do a line check. Make sure you label your line check. Left to right, negative 1, 0, smallest to biggest, test a value. I'm going to test x equals 1, positive, negative, positive. And draw little arrows showing slopes. Increasing, decreasing, increasing. This is a relative max. You can see it's peak. This is a valley. Relative min. So there is a relative maximum at x equals -1. You want to say it's at, don't say it is. The relative maximum value is the y value, which we could find if we wanted to. We often aren't asked to, so I don't force myself to do it unless I know I need to. Relative minimum at x equals 0 again. Now, I'm not going in depth here with justification, but those are the answers. Okay. Next one. Now, these typically have domain issues, so watch out for this, right? I mean, you just always need to watch out for it, but there's certain times where it's super obvious. Now, this, if you were to solve for it, it's plus or minus I, so it has no roots. So you could test it. You know, you can still test it without any roots. X equals 0. It's positive. It's true all the time. So domain is -infinity, positive infinity. But be on the lookout. Okay, y prime equals 1 over what's inside, natural logs, times derivative what's inside. So we get 2x over x squared plus 1. We're going to set it equal to 0 undefined. X equals 0 on the top. X equals plus or minus I on the bottom, which we're not going to use, but I want to see evidence that you thought about it. So we're going to do a line check. 0, test a point. X equals 1, positive, negative. Little arrows with the slopes, decreasing, increasing, relative min. So there's a relative minimum at x equals 0. That's just the answer. If you want to justify it, say by first derivative test for relative extrema, since y prime is negative for x less than 0, y prime is positive for x greater than 0. Now, number 4 is kind of interesting. It's going to kind of lead into what we're going to be talking about today for the first time. If f of x is continuous and differentiable, those are important things. That means that it's all connected, no holes, jumps, vertical asymptotes. Differential means smooth, no corners or cusps. And they're giving you a limited amount of information. They're not giving the actual function. They're telling you, well, here's the value. The y value at x equals 2 is 3. The derivative is 0. And the second derivative is 5. Can it be determined if there's a relative maximum or minimum at x equals 2 with this limited amount of information? Well, I don't know. Let's think. Do we know anything special here? This, you should be like, ooh, that's a critical point. That's like a peak or a valley, right? Peak or valley. But I don't know which one, right? This is concavity. This is telling you that it's concave up at that point. So we know we have a flat spot. We know it's concave up. So generically, it's going to look like this. We have a flat spot at x equals 2, right? The derivative is 0. The second derivative is positive. It's concave up. I'd say that's a low point. That looks like a valley, right? I'd say for sure that's a relative min. So I think we can. I think we can say there's a relative minimum at x equals 2. Now I can't say it by first derivative test because I didn't use it. I don't really know what the slopes are on either side. So this is where we're getting in the second derivative test. Now you got to watch out. F prime, if f prime was 0 at like a plateau, then it wouldn't be a peak or valley. But then again, there wouldn't be any concavity there. The concavity would be 0. And if it were a critical point this way, this wouldn't work with second derivative because second derivative doesn't exist at a corner. So anyway, some things to think about, but we're gonna get into that right now. Okay, so second derivative test for relative extrema, relative max is min. So essentially, it's what we're doing. It says if x equals 8 is a critical point. So you know that f prime of x equals 0 or undefined, right? For f of x, and f double prime is If it's positive, then that's concave up, right? And so that would be this kind of case right here. So this isn't something to memorize, just sketch a picture. If it's concave up and you have f prime equals 0. Now, by the way, it can't be defined because there is, if f prime is undefined, f double prime is going to be undefined. And this requires that f double prime has value positive, negative, concave up or down. So in this case right here, it's got to be a relative minimum. It's got to be the low point, right? It's got to be a relative min. Now, if f double prime was negative, then it would be concave down, and we would get a relative max. So concave down, f double prime is negative, concave down, and you know you have a critical point, slope is 0, then that has to be your relative max, right? So this is the second way to do what we already know how to do using FDT, first derivative test. And we usually want to do first derivative test. Second derivative test is usually more work. You got to do extra derivatives. You first of all have to identify, you got to do all the work pretty much you got to do for first derivative test and then more. So it's not really a great alternative. It's usually more for when you have no other choice, like on problem 4, the warm-up. We couldn't do first derivative test. But again, this is not, you don't want to memorize all these different cases. Just draw a picture. Be like, okay, is it a relative max or min? If it's concave up or down, just draw a picture and be like, oh, concave up, we're at the bottom. Concave down, we're at the top, right? Now back to problem 1. Let's see if we can do it this new way. Y equals x to the 4th minus 4x cubed minus 1. So we already did problem 1 using first derivative test, but let's use second derivative test just to show how it works. We first have to take the derivative for x cubed minus 12x squared, like we did before, equal to 0, undefined. Still have to do that. Still got to factor it, take out 4x squared. And we get x equals 0 and x equals 3 as our critical points. So we still got to find the critical points. Now, the one thing we're going to do is we're going to skip the first derivative line check. And now we're going to go to the second derivative. So the second derivative, this is what we didn't have to do before, would be 12x squared minus 24x. We're going to set it equal to 0 undefined. And then we're going to factor it. Take a 12x out, x minus 2. And we get x equals 0 and 2 as possible inflection points. And so then you would then find what the second derivative value is there. So x double prime of 0 is 0. So that's not going to be, that's not a relative max or min. By the way, we kind of knew that was the case. It's a plateau. Not a relative max or min. Y double prime at 2 is going to give you 48 minus 48. Does that make sense? Okay, I think I made a mistake here. Let's see. Oh, okay, we're testing the critical points. That's what we're testing. That's what we're testing down here. We don't really care about inflection points. So if you plug 0 in, if you plug 0 in up here, you get 0. If you plug 2 in, you get 32 minus 48, which is negative 16, which is negative, and so that means that it's concave down. And again, don't memorize it, just draw a little quick picture, and you're like, oh, okay, well, that has to be a relative max. That's got to be at the top. So we'd say, I think I made another mistake. Okay. If we plug 2 in here 8 times, I feel like I'm plugging this into the wrong spot. Oh, okay. Man, I keep doing the same thing. It's supposed to be 3. So 3 is me 27, 54, 108. Gosh, 108 minus 10, and you plug 3 in here, that's 9. That's 108. don't know why I keep getting messed up here. 3 into this. Okay. 990, 108. Oh, jeez. Gosh. Okay. Sorry, keep getting thrown off. You got to plug these in the second derivative. So that's going to be 108. And you plug 3 in here, and that's 72. And so you get 28, 36, which is positive. So it's concave up. Concave up. And you have critical point. So that's got to be relative min. All right. So we have a relative min at x equals 3 by the second derivative test. So you'd have to first verify that it was critical point, and then you'd have to say what the concavity was, and then you can make that conclusion. Okay. I mean, that was more work than the way we do in the warm up. I'd rather do it the warm up way. Okay. Unless I had no choice, like a number 4 the warm up. Now, there might be an occasional example where the second derivative test has its benefits, but rarely. So here's the first derivative. Say equals 0 and define. So x equals 3 is your critical point. And second derivative is 2, which is always positive, which is always concave up. So I guess we just jump to, okay, we know it's a relative min. There's a relative min at x equals 3. A little quicker because the second derivative is constant, right? But usually we're not going to do it unless we have to. Now, on today's homework, I think you might be asked to do it just to practice it. Even on problems that you could do the first derivative, or even asked to do it both ways. Okay, so let's take a look at the back here. I'm going to try and make some more connections. Now, we're going to start to be looking at graphs of derivatives and second derivatives and trying to get information from them. So just with a graphing calculator, I'm just going to kind of show you some stuff here. So I'm going to put this in here, x to the third minus 6x squared plus 3. Now, this is a cubic, right? So you guys should know what the graph's going to look like. I'm going to say negative 10 to 10, negative 10 to 10. Just try that quick. So here's cubic. It might be nice to see what's down here. So window, I go negative 5, negative 20. So I'm kind of changing my graph a little, maybe a little further down. Window, negative 30. So graph kind of looks like this. That's the original function. Now the derivative, just doing the derivative ourselves, is 3x squared minus 12x, which is going to be a parabola. Now that graph's going to line up to some special places. So like the derivative here should be 0 and here should be 0. So that should translate to x-intercept and x-intercept on the derivative graph, and it's going to be a parabola opening up. Now what I can do is I can make this graph darker by hitting enter. So it kind of stands out. And then 3x squared minus 12x. And we could graph it. So here's the first graph. And then here's a parabola that gets graphed. So sure enough, it goes through here. And it goes kind of like this. So this is the original graph. And I want to put these next to each other because I want to start to show you guys some of the things that line up, okay? So, the peak lines up right here. This is y prime, this is y. And so right here the slopes are positive, right? And this is positive, y prime is positive. And here the slopes are negative, and sure enough, this whole chunk of graph, y prime is negative. It's all below the x-axis. And then here the slopes are positive, and y prime is positive. And then the 0 slopes right here, these are automatically going to be critical points on your derivative graph. X-intercepts are going to be critical points. And we could do first derivative test. We could say, oh, look, derivative's going from positive to negative. That must be a relative max. And sure enough, it lines up to that relative max here. And this should be the location of a relative min. It goes from down to up. Negative derivative, positive derivative. And sure enough, it lines up with the relative min. right? So we can use the derivative graph even without having a picture of the original graph to identify these special things. Now the second derivative should give you concavity. So we have this inflection point right here, right? It goes from concave down to concave up. So all of this should be below the x-axis, and all of this should be above the x-axis for the second derivative. So we could put that in there, 6x minus 12, and we can make this one like, say, dashed. Like that, a little more dashed. Oh, so it's a line, right? It's a line now. Every time you take a derivative, it takes it down a degree. And right here, this is its x-intercept, and it kind of goes like this, right? It goes like that. And sure enough, here, this is where all the second derivatives are negative on the original graph, right? That's where it's concave down. Here, second derivatives are all positive because that's where it's concave up. And here's your inflection point. It lines right up with that inflection point. So I know it's kind of a mess. We're doing a lot of different stuff, but can you find? Let's take a step back and say, can we find the relative max and min from the graph of y prime? So if we, I graphed it. I said it looked like this was the graph here, right? And if you just graph y prime, this is where y prime is positive. This is where y prime is negative. This is where y prime is positive. This is a critical point because y prime equals 0. These are y prime values being graphed here. Here's another critical point. It goes from positive to negative, up to down. This is a relative max. And then you're going down, negative slopes to positive slopes, going up, down to up, down to up. It has to be a relative min. It has to be a value. So we can totally get that information from there. How about from the second derivative? What could we get from there? So let's say from the second derivative. So the second derivative ended up being just this line like this, right? And what this tells you, it tells you that f double prime is negative. So it tells you that it's concave down here. And here, f double prime is positive, so it's concave up here. And this is an inflection point because it's changing from concave down to concave up. So that's what the second derivative graph could give you. So f is the y values, f prime is y values of f prime is the slope of f double prime is the concavity of f. But now we're looking at the slope of fx. In this problem right here, the slope of the graph equals the actual y values on this graph. The y values on this graph, y values of f prime, right? And then the concavity is going to be the slope of the f prime graph. So if I have this, you could tell me, oh, it's concave down from here to here because this is all going, the second derivative is going to be negative because the slope of the first derivative is negative. F double prime, the second derivative, is the derivative of the first derivative. So if you're looking at the first derivative graph, you can get concavity, concave down, concave up. It's not concave up the whole time. This is not the original graph. Concave down, concave up, inflection point. So we're going to start to practice that. We're going to start to try and sketch graphs either way. So this is sketch f from f prime. So we're going backwards. So this is the derivative graph. And I want to try and sketch the original graph. So we've been talking about how to get information about it, but let's actually draw a picture of it. So some things to ask yourself, well, I would actually answer these afterwards. So what I would do, I would say, okay, let's first identify critical points, right? Critical points. All right. And actually, I'm going to line these up. And when you're trying to go backwards, you really only need two things. I mean, we're going to do really rough graphs. I mean, we could make them better, but For each chunk of the graph, I want to know, we got to start at some arbitrary C value. So I don't know if you guys remember from pre-calc, if you did any pre-calc, a little bit of calculus integrating, you have to start at an arbitrary point C. We call it the constant of integration. And it's an issue when we integrate, which we have not done at all this year, really. Our calculator's done a little integration. But you can imagine that if you have some function y equals 3x squared plus 5x plus 3, when you take the derivative, you get 6x plus 5, and this just goes away. It's a 0. So if you're trying to go backwards and you're trying to undo the derivative, which is kind of what we're doing visually, how are you going to know what should be there? It could be a 5, a 3, a 10, a negative 50, or nothing. And so that's where we put like this C value here, just because we're not really quite sure. So it's got to start at some point. Now, the only questions I want to ask myself is, are we going up or down, increasing or decreasing, uphill, downhill, okay? And is it concave up or concave down? That's it. That's all I'm asking. So we're going to start here. This chunk is decreasing. Look, increasing, increasing, decreasing, because this is where f prime is negative, right? Here, this is where f prime is positive for all of this, because this is the graph of f prime. So that's one thing right away. And then the concavity is, well, the slope of this from here to here is concave up, because f double prime is positive for all of this, because the slope of the slope. And here, f double prime is negative, concave down. And here, f double prime is positive for this whole chunk, concave up. And here, f double prime is negative, concave down for this whole chunk. That's all I really need to sketch the graph, is increasing, decreasing, concave up, down. So here, we are concave up this whole time. So we are decreasing and concave up. So the graph has to go down and be cupped upwards. And then we're increasing and concave up. So the graph goes like this. It should be a smooth graph. And then we're increasing still, but concave down. Right? And then here we're increasing still, and then concave up. And here we're increasing still, but concave down. And here we're decreasing and concave down. So that's a quick sketch working backwards. If you sketch the derivative of graph of this, you would get this. So that's something we're going to be doing more of coming up soon. So today's assignment, so even from this, you could kind of answer a lot of questions. Like I know just from this graph, it's going down then up. This is relative min. And sure enough, look what we got on our sketch. And I know this one, we're going up then up. This is neither relative maximum, it's like plateau. Sure enough, plateau. This one, we're going positive slope to negative slope, up then down. This is a relative max. Sure enough, got a relative max. Inflection point where concavity changes. Well, concave up to concave down, that's an inflection point. Inflection point, inflection point, inflection point. And sure enough here, inflection point, inflection point, inflection point. So we have inflection points at x equals 2, 3, 4. Relative min at x equals 1. We have relative max at x equals 5. All right, today's assignment out of your textbook. Try these out. A lot of evens, so I should probably put the answers online for you. Check those. Check the odds in the back of your book. That's it.